Welcome to lesson 3.2b, the least squares regression line. Usually right now you'd be watching a video of me, but today you don't get that because I've been cleaning house and decorating for Halloween all day and I look horrible. So now you're just going to have to listen to my voice and be happy that you don't have to look at me. So we're moving on with lesson 3.2, and this is the second part of 3.2, I believe. And we're going to be talking about a regression line. Now, originally we were going to do lesson 3.2 in one section, but we are actually going to do it in two. After reviewing the quantity of information I needed you to learn, I decided that we need just to slow down a bit so you truly understand regression. Now, most of you have been exposed to regression lines because we've used regression lines in the past and we just found out how to find them on our calculator. But let's talk a little bit more about what a regression line is and then how we use it. So first of all, I got a new stylus today. Let's see if it works. A regression line All right, here's an example we'll be using throughout this section, and this is about non-exercise activity and its relationship with fat gain in kilograms. Some people don't gain weight even when they overeat. Not me. Perhaps fidgeting and other non-exercise activity, we call this NEA, explains why some people may spontaneously increase non-exercise activity when fed more. Researchers deliberately overfed 16 healthy adults for 8 weeks. They measured fat gain in kilograms as the response variable and change in energy use in calories as the explanatory variable. And here's the data. Now, this is specifically just measuring activity that people just naturally do. So, for instance, if you're one of the people who listens to lectures and has to move constantly, fidgeting, shaking your knee, tapping on the table, that would be called non-exercise activity. So you see that right up here. Let's bring out the, why is this not working? I still have my lightsaber out. The NEA changed. We can see the non-exercise activity calories being used and the fat being gained. And we're going to take all that and put it into this nice little line here. I was feeling the need to have some volume on this. Oh, there you go. All right, so we see this line that we get by calculating it out. And in this section, I'm going to talk to you about how we actually get this line, this regression line. How does a calculator find this? And in a bit, we'll find the equation of a line in another type of a way. All right, so here's some more important vocabulary for you. A regression line, predicted value, slope, and y-intercept. So suppose the y is a response variable plotted on the vertical axis and x is explanatory variable plotted on the horizontal axis. A regression line relating y to x has an equation in the form of y hat equals a plus bx. Now, this y hat thing is super important. Y hat means prediction. Just remember that. So, for some reason, this didn't carry through well. But y hat, if you need to write this down, you can. So you know that this is y hat. We'll be doing a lot of things that have hats on them for predictors. Y hat is the predicted value of the response variable given an explanatory variable. Sorry, ran out of space. B, obviously you should know by now, is the slope. And it's the amount of change that is predicted when x increases by 1. And then last we have the y-intercept. And this is the point, the predicted value when x equals 0. I wonder if that is going to come up when you see this video that I just got a text message. It would be very interesting if it did. I bet it does. That's funny. Okay, so x equals 0 at the y-intercept, but you already know this. Here's a little bonus Byrie knowledge because I think it's important that I tell you a few things. On the AP exam, when writing the equation of regression line, often students will forget to put the hat on the y hat. This is really, really important because remember that y is the actual value of y, but y hat is the predicted value of y. We are getting a predicted value by using a line of regression. Now, often this is something that you'll miss on the AP exam and you will lose points. So you lose points when you just put y. They are two different things. You need to know they are two different things. All right. Also on the AP exam, the least squares regression line, which is what we're going to be looking at, is a formula that's written like this. It is no different than this. It's exactly the same thing. But on the AP exam, they just use this form. All I want you to do is understand that you don't need to freak out about it. It's exactly the same thing. You already know it. All right, so guided practice. Identify the slope and y-intercept of the regression line and interpret each value in the context. Well, I need to give you the regression line. So the regression line is as follows. Oh, let's have a prettier color. Fat gain. Well, it would help if I could spell. Try this again. Fat gain, and this is fat gain hat, equals 3.505 minus 0.00344, and then it's your NEA change. So fat gain hat, in other words, the predicted y value equals 3.505 minus 0.00344. So what is the slope? Well, it is negative 0.00344, which is the fat gained goes down 0.00344 kilograms for every or each 1 calorie of NEA that's burned or NEA that's used. I don't know. That's a slope. And the y-intercept is A, which is 3.505 kilograms, and that is the fat gained when NEA does not change. Or basically when there's no NEA at all, no non-exercise activity. So now they want us to use a regression line to predict the fat gain for a person whose NEA increases by 400 calories when he or she overeats. Well, fat gain, again, I'm just going to put fat, equals 3.505 minus the slope of 0.00344 times 400. And what we get is 2.13 kilograms. So a person who increases their NEA by 400 calories when he or she overeats will gain 2.13 kilograms of weight. Now, a couple of key vocabulary words: interpolation and extrapolation. And what we're really basically, we can remember that inter is within and extra as without. So this is, when we use interpolation, we are going to predict with the regression line for an x or explanatory variable within the range of the data, specifically the data used to get the regression line. Therefore, if we're going to interpolate, we are going to use a data point that is within the range. It may not be an exact point, but it's within the range of data that we're looking at, within the range of x's. Now, if we're going to go outside of that range, then we're going to do some extrapolation. And so this is predicting, again, with the regression line for an explanatory variable, or an x, outside of the interval or the range, let's just say outside the range of data specifically for your x values. So here's the problem. When we go outside of the range, these are usually not accurate. And I'm going to show you an example of that next. So, wow, this thing completely freaked out. This is not good. I have no idea when I don't know what this thing is doing. Okay, I don't know exactly what this slide did, so I'm just going to put it over here. And you will have the slide in front of you that you can just use. So I'll just write on this area out here. So we're looking at rats in this little example. Some data were collected on the weight of a male lab rat for the first 25 weeks after its birth. A scatter plot of the weight in grams and time since birth in weeks shows a fairly strong positive linear relationship. The linear regression equation of weight hat equals 100 plus 40 times time. And it models the data fairly well. So the first question we're asked is, what is the slope and y-intercept, and interpret? Well, the slope is 40, and that means that the rat is going to gain 40 grams per week. The rat will gain 40 grams per week. And the y-intercept is 100. So this is the expected or predicted birth weight of a rat. All right. Question number 2 says, predict the rat's weight after 16 weeks. Okay, well, weight, and I'm just going to say weight hat, is 100 plus 40, and we want to know after 16 weeks, so we're just going to plug in 16. And if you do that math out, you get 740 grams. Okay, 740 grams. I don't really know how big that is in real life, but that seems to be something that completely makes sense. Now, let's look at why we might not want to use this to predict after 2 years. So we're going to convert 2 years to weeks, which would be 104, right? All right, and then we would plug that in. Now, if you plug that into our equation up here, what you get is y hat equals 4,260 grams, which is about 9.4 pounds. Now, I don't know about you, but a 9.4-pound rat does not sound appetizing to me and kind of creeps me out, especially since it's October and, it's October and there's weird people in Bakersfield, California dressing up as clowns and carrying weapons. I'm telling you, there's some sick puppies out here. So 9.4-pound rats, that's like bigger than my dog. So there you go. This is why we don't want to use this. The rat will not continue to grow. There's a time at which all things stop growing. So it would be unreasonable and frightening. All right, so that's an instance where extrapolation is just not a good plan. Just don't do it. All right, now we're going to move on to residuals and least squares regression line. A residual is an incredibly important part of statistics, and it's not that difficult, but it's just something that you have to visually see. A residual is the difference between a predicted line and the actual data value. So you can see here that we have a data point, say here, and we have a line, a regression line here. Now the line is the predicted values for everything, for y. But we can see that the actual data point in that regression line is quite a bit away. When we take this difference, we get what's called a residual. So a good regression line makes these vertical distances or residuals of the points from the line as small as possible. All right, residuals are the difference between the actual or observed and predicted values of the response variable. And we find these by finding the residual is equal to y minus y hat. Observed minus predicted. Now, distance and direction are really important, because if you get a residual of -15, then you are saying that you are 15 below the predicted line. Likewise, if you get something that's positive, you're saying that you are above the predicted line. Sometimes our data is lower than predicted or higher. So it's very important that in residuals we're telling both the distance from the line and the direction. In addition, there's another type of regression line which we're going to use, and this is called the least squares regression line. Now, you can see here that we have our residuals. And what we do with the least squares regression line is we square these residuals and we add them all up. Now, what that does is anytime we square something, what do we get? Positive numbers. And once we start squaring things and adding and subtracting, we should get 0 if we add all of these squares up. I'm sorry, if we add all the residuals up, we get 0, but if we square them, then we get a little bit more information from the line. So the least squares regression line least squares regression is a line of y on x that makes the sum of the squared residuals as small as possible. I got a new stylus today, but this thing squeaks. I hope it's not bothering you guys. Again, another slide that did not come through. So let me change this one again, just like we did before. You have the correct printout because your notes are proper. So the equation of the least squares regression line, if we have data on an explanatory variable x and a response variable y for n individuals, from the data, we want to calculate the means x bar and y bar, the standard deviations s of x and s of y of the two variables and their correlation. And if we do that, the least squares regression line is the line that says y equals a plus bx. The cool thing is, if we have the information, which we can usually get from a calculator, we can find the slope ourselves. So we would find the slope by doing b equals r, which is the correlation coefficient, remember, times s of y over standard deviation of x. And the y-intercept we find by using our 2 points, x bar and y bar, our means. So our y-intercept is equal to y bar minus b times x bar. It's actually really handy that we're able to find the equations of the line just like this. So let's do one example and you'll be done for the night. Okay, again, another bad slide. So hopefully you can see these in your notes. Let's just put that down here. I don't know what went on today. Crazy, crazy, crazy. Let's choose some pink color. Okay. So we're going to use the data from the beginning of the lesson about NEA and fat gain. And we want to use a couple of things. So the mean of the NEA, which remember is our explanatory variable, x bar is 324.8 calories. Our standard deviation of x is 16 fat gains. Our mean of our, our fat gain is 388 kilograms. And my standard deviation of y is 1.1389. Now my correlation coefficient for this bit of data is negative 0.7786. So let's find the equation of the least squares regression line for predicting fat gain from NEA change. All right, we can do this. So here we go, part A. Well, first of all, we want to find the slope. So remember, slope is found by taking the correlation coefficient times standard deviation of y over standard deviation of x. Well, since I've already given you all these numbers, it's not hard to figure out. I get negative 0.7786 times 1.1389 divided by 25. Where did I put that? No, what did I do? Oh, I told you the wrong thing for the fat gains. Let me change that because I'm not paying attention to what I'm doing clearly. Let's change this to the actual number, shall we? That sounds great. All right, that was 257.66. All right, 257.66. You guys can read it. It's in your notes right ahead of this. All right. So what we're going to do is just find the equation. So we've got B equals, if we work all that out, we get negative, this should look familiar, 0.00344 kilograms per calorie. Now we've got our slope, so B equals the negative 0.00344. And now we're going to find the other part. So remember, x bar and y bar are 324.8 and 2.388. Man, I got like crazy. Oh, yeah. I know what I was doing. I was not writing down the right numbers. All right, and so we're just going to plug this into our equation. And our original equation, remember, is y bar equals a plus b of x. So plug it in. I get 2.388 equals A, I don't know what that is, plus negative 0.00344 times 324.8. Now I know that you can work all this out, and when you do, A is equal to 3.505 kilograms. So our equation is y hat, let's change colors. Y hat equals 3.505 minus 0.0034x. This should look like the equation I gave you at the beginning of the chapter, but we actually did this ourselves and showed you how to do it. Now it says, the last part, what fat gain should we get if we, let's go back to blue, what change in fat gain does the regression line predict for each additional 257.66 calories of NEA? Well, an increase of 257.66 calories, we're just going to plug it in using our regression line, 3.505 minus 0.0034 times 257.66. And what we get is negative 0.89 kilograms. So what this is saying, there is a decrease of 0.89 kilograms for every 257.66 calories that are used. And that is how you use a simple regression line. Our next lesson, we will be continuing on with regression lines and deciding how well data actually fits a regression line. So I hope that this made sense. I hope you understood it. Please take the time to really get this down. It will make next lesson so much easier. And I promise by then you'll be able to see my face. We'll see you in class on Thursday. Have a great week.